everybody. Today I'm going to explain you about complex compounds. So, transition elements have the transition metal ions or the atoms, they have a tendency to form coordination compounds or complex compounds. A complex is formed when certain number of molecules or negatively charged ions, that is ligands, surround the central metal atom, and the surrounding molecules or ions possess a lone pair of electrons and form dative covalent bonds, the metals. So such type of compounds are called complex compounds. So complex compounds are coordination compounds, are the compounds. These retain their identities even when dissolved in water or any other solvent. And the properties are completely different from the constituents. The tendency of the transition metals or the atoms to form complex compounds, there are different reasons. So transition metal atoms form complexes due to relatively small size of the metal atom and they possess high positive charge. This makes it easy to accept electron pairs from the ligands. So transition metal atoms, they are relatively small in size and possess high positive charge. This makes it easy to accept the electron pairs from the ligands. So, and these metal atoms, so these metal or the cations, they have low energy, unfilled d and p orbitals. These can accept a pair of electrons from ligands to form a dative bond. And transition metals have ability to show variable oxidation states. So therefore, these elements or these metals are able to form the transition metals. Due to the size, low size, high positive charge, easy acceptance of electrons from ligands, and these have low energy filled d and p orbitals, accept pair of electrons from ligands, form dative bond, have ability to form the various oxidation states. So a complex ion consists necessary counter ions. That you can see cobalt, pentamine, chloride. So the complex ion, this is the complex ion within this plate. Cobalt, ammonia, and chloride. This is the oxidation state. So the counter ions are, these are the counter ions, the ones which are outside. Species where transition metal ions is surrounded by certain number of ligands. There are the species where transition metal it is surrounded by certain number of ligands. So transition metal atom, it is the Lewis acid, and the ligand is in space. This is the Lewis acid and this is the base. This is the Lewis acid and this is the bases. They get different charges. So some of the important terms that are involved in the complex compounds, central metal ion. The central metal ion or the cation, the central metal ion or cation, to which one or more anions or the neutral molecules are attached by coordination bonds are called central ion. Central ion is the acceptor which have empty orbitals. And the ligand is an atom or ion or the molecule capable of donating pair of electrons to the central atom is called a ligand. And coordination sphere, the total number of ligands attached to the central metal ion is the coordination number. This is the coordination number. And what is coordination sphere? The central metal atom and the ligands directly attached to it collectively is the coordination sphere. They are enclosed in the square brackets here. This is coordination sphere. This is the central midline. These are the ligands. And this is coordination sphere. And 5 plus 1, 6. This is the coordination membrane. And this is the oxidation state. So complex ion is electrically charged. Complex ion, it is electrically charged, or neutral species formed by combination of central cation with more than one ligand. So coordination compounds and shapes of some of the complex molecules are given there. If hybridization is coordination number is 2, hybridization is sp. The geometry is linear, 180 degrees bond angle. 180 degrees bond. Here are some of the examples. Next, if coordination number is 3, it's not given here. sp2 hybridization, trigonal plane. 120 degrees is the bond angle. Here and here happens some of the examples, mercury iodide. Now the next one is, if coordination number is 4, hybridization is sp3 and shape is tetrahedral. So the shape. Bond angle here it is 109 degrees 28 minutes. And here are some of the examples. Cadmium tetrachloride, manganese tetrachloride, copper cyanide, zinc tetramine. Now, here not given for you, the coordination number is 5. The hybridization is dsp3. The shape is trigonal and bipyramidal. You have 90 degrees bond angle, 120 degrees bond angle. Trigonal bipyramidal. Penta-iron carbonyl is an example. Pentacarbonyl iron is the example. Let's come to the next one. 6th, coordination number 6. Hybridization is D2sp3. Octahybrid. 90 degrees is the bond angle and 90 degrees. Here are the examples. Exact what I did. These are the complex ions numbers with complex ion coordination numbers and shapes. As I've told you, the molecule or the ion having no electrons that can be used to form bond is a Lewis space. Coordinate covalent bond, metal ligand, monodentate. If one bond to the metal, then that is monodentate. If 2 bonds to the metal, then that is bidentate. If it is 3, then that is tridentate. So on, if it is more than 2, then it is coordinated. Next, ligands and the coordination compounds. Here, unidentate ligand. Examples: water, ammonia, fluoride, chloride, cyanide, isocyanide, thiocyanide. Okay. And hydroxide nitride. Coming to the bidentate ligand, ethylene diamine, oxalate. Polydentate ligands, diethylene triamine, triphosphate, ethylene diamine tetraester acid. So these are the ligands. Now formulas for the coordination compounds. So cation and their anion. First you have to name cation, then anion, nomenclature. Total charge should be balanced to zero. Complex ion should be kept in the brackets. First cation, then and this is complex ion in the brackets. Potassium tetrachloride, cobalt. Yeah. Tetramine cobalt chloride. Names of the coordination compounds. First cation, then you have to name anion. Next, ligands you have to do in the order of the alphabetical order. Before the ion, the alphabetical order automatically. So cation, then anion should be named. More than one if it's possible, then we have to. It can be possible, so in the brackets. Complex ion is equal to anion, metal ion, AD. Next, names of some ligands. Names of some of the ligands. Here, neutral ligands: aqua, amine, carbonate, nitrogen. Aqua, H2, amine, NH3. Carbonate, carbon C, captain C, captain. If it is nitrogen, N. If it is anionic, fluoro, F minus. Sclero, C minus. Br minus. Iodo, I minus. Hydroxide, OH. Cyano, C minus. Name of some of the metal ions in the complex ions. Center metal ions. It is iron ferrite. It's copper cuprate. It is lead plumbate. If it is silver argentate, 8 has to be used as a suffix. Gold orate. Tin stannate. Examples: K2CO NH3 twice Cl4, potassium, diamine, tetrachlor, cobaltate, 2. Your ammonia is 0, the oxidation state is 0, and chlorine is -1. So you get -4 with respect to 2. And here you have potassium 2. Charge is +1, +2, +2 into -4 you get cobalt charges 2. And similarly, tetramine here, tetramine dichloro cobalt 3 chloride. That's the way we name. And there are some rules here which govern the naming of the nomenclature of the compounds. First, those IUPAC rules are: cation has to be named first, and non-ionic complexes. Non-ionic complexes are the molecular complexes are given by one word name. In the complex, the oxidation state of the central metal is indicated by one brackets, and immediately after the metal. The suffix "aid" is to be added to the name central metal for anionic complexes. In The cationic complex is the usual name of the metals followed by the oxidation state of the metals. Now, the next rule is you have to name the coordination sphere. So, cation and the non-ion complexes were named, and in the complexes, the oxidation state of the central ion should be indicated in the round number. There you can see in the example. And the suffix 8 is to be used. The suffix 8 is to be used for the central metal ion. For the cationic complexes, usually the name of metal is followed by the oxidation state, as I've told you here. And naming of the coordination sphere. Ligands are named first, then the metal ion. Neutral ligands are named as the molecules, and neutral ligands are named not as the molecules. Example: EPH3 triphenyl phosphate, PY pyridine, that is 2-actin. And for negative ligands, we have to put fluoro, hydroxo, amido, nitrito, nitrato, imido, oxalato, carbonato, sulfato, nitrito. So, next, for the positive ligand, it should end EM, IUM. It should end with IUM. Next, the different types of ligands in the complex is named in the order of negative, neutral, positive, without any separation. If for positive ligands, IUM should be used. Nitrosonium, hydrazinium, and that. And different ligands in the complex named in the order of negative, neutral, positive, without any separation. Trichloro, triamine. If similar ligands more than one is there, you have to use di, mono, etc. Next, in case of the chelate ligands, more than one, the number is indicated by the prefixes bis, tris, tetra, is like that. In polynuclear complexes, bridging ligand is denoted by prefix. In polynuclear complexes, bridging ligand is denoted by prefix mu before its name. In case of ambident ligands, the donor atom is designated in bracket of its name. So, example, yeah, in case of ambident ligands, donor atom should be designated in the brackets after name. Potassium hexathiocyanate and cobalt. So you can write the name of the complex compounds. At the same time, you can write the structures of the compounds depending on the names. Now, Alfred Werner, he has given a theory about the coordination compounds. How the coordination compounds, complex compounds are formed. How the coordination compounds, complex compounds are formed. To explain the bonding and properties of the complexes, these theories were emerged. First one is a Werner theory. The second one is a Stitchburg theory. The third one is a Valspont theory. And the fourth one is a restrictive theory. So here you are having the Werner's data for the theory. So primary valence of the metal is the oxidation state of the metal. Primary valence of metal is the oxidation state of the metal complex. And this is the ionizable valence. Primary valency is seen in the simple songs. Secondary valency is the number of monodectic ligands attached to the central nucleus by coordination. Primary valency is always satisfied by negative ions, while secondary valency is satisfied by the negative ions of the neutral molecules. Every metal has number of secondary valency, fixed number. Second valency is always the coordination number. It is always the coordination number. Secondary valency is directed towards a fixed position in the space about the central. Hence, the number and the element of ligand space determines the stereochemistry of a complex. If 6 ligands are present, complex have octahedral structure. If 4 ligands are present, it is tetrahedral or square planar. So, the structure here, the cobalt complexes represent the secondary as well as the primary valency. Secondary valency by the thick line and the primary valency by the thin line. Once seeing the data, once if you dissolve this molecule in water, the total number of ions are 4. Here the free ions are 3 chloride ions. So the modern formula is this one, and the charge is +3. Once if you add silver nitrate or solvent, 3 chlorides come out. This is the primary valence and this is the secondary valence and this is primary. Similarly, if one ammonia is removed, another chlorine replaces the secondary valence. So total number of ions get decreased to 3. The free ions are 2. Yeah, this is the formula. Putting silver nitrate, you get 2 chlorides. Next, cobalt chloride tetramine. Total ions 2. Free ion is 1. 1 ammonia reduced, 1 chlorine replaces 2. Here 1 ammonia got reduced, and here 1. So total of 2 ions are getting reduced. Total of 2 ions are getting reduced. And thereby 2 chlorines get the secondary valence. On dissolving you get only 1 chlorine outside in the silver nitrate. In the silver nitrate, you get only 1 silver chlorine. Only 1 is the primary valence. Coming to cobalt trichloride, triamine. The total number of ions 2 and the free ions is 0. So total of 6 ammonia should be there, only 3 are there, 3 potentials. 3 chlorides are getting, and the 3 chlorides are getting here for the secondary valence. So here the charge is 0. Now let us see the isomers in the compounds. What are isomers? What are isomers? Compounds having same molecular formula. Here in coordination compounds, we can tell about the compounds having same molecular formula, complexes having same molecular formula, but different atom arrangement are called as the isomers. Now, these isomers are divided into 2 types: constitutional structural isomers and stereoisomers. Yeah, structurally, if there is any difference, but the formula is the same. Here, then atoms connected differently. Here, constitutional isomers, structural isomers otherwise, atoms connected in different ways. They are called as structural isomers. In structural isomers, you have linkage isomers, coordination isomers. So we'll see. So yeah, there is slight disturbance in the voice. Again, I'm repeating. If the molecules have same molecular formula, different atom arrangement, then they're called as the isomers. Compounds having same molecular formula, chemical formula, different structure, they are the constitutional isomers. And phenomenon is known as isomerism. Isomerism in coordination compounds can be classified as you can have structural and stereo. The isomers that are arising due to difference in the chemical linkages and distribution of the ligands within or outside the coordination sphere, they are structural isomers. And isomers in the coordination compounds are the structural isomers are ionization isomers, hydration isomer, linkage isomer. Okay, yeah, the same is written. Yeah. The isomers, structural isomers with different bonds, different due to difference in the type of the chemical linkages and distribution of the ligands within and outside the coordination sphere. So ionization isomer you're having the structural isomer again further divided. Ionization, hydration, the linkage, and coordination isomerism and coordination position isomerism, polymerization isomerism. So in the structural isomers, if the isomers have same composition but leverage different ions are ionization isomers. And the isomers having same formula but differs in the number of water molecules attached to the central metal atom is hydration isomerism. And the type of isomers that arises due to presence of ambidentate ligands, which have different donor atoms in the same ligand. They are the linkage isomers. And the isomers which contain both cationic and anionic complexes and results from interchange of the ligands between the two complexes of the same complex are coordination isomers. Coordination position isomers. In this isomers shown by bridge ligands arising due to difference in the attachment of the ligands to the metal. So polymerization isomerism, complex having same empirical formula but differing the molecular weight is polymerization isomers. Now coming to the next one, stereoisomers. They have same bonds, different special arrangements. Same molecular formula but different special arrangement of group atoms are stereoisomers. In these stereoisomers, isomers have same molecular formula. Yes, compounds having same molecular formula, different spatial arrangement of atom groups are stereoisomers. These are divided into two types, geometrical and optical. Coming to the geometrical isomerism, cis-trans isomerism. Isomers have same molecular formula, but ligands occupy different positions is geometrical isomerism. If two identical ligands are adjacent to each other, and the isomer is called cis. If two identical ligands opposite to each other, then that is trans isomer. This isomerism, you can see the square planar complexes coordination in the four. And you can even observe in the complexes, octahedral complexes of coordination in the six. So, here is an example for the coordination isomerism. In the structural isomerism, coordination isomerism, here is an example. The isomers which contain both cationic and anionic complex. And on interchanging the ligands, sulfate and bromine sulfate, interchanging the ligands between the complexes of same complex are called as the coordination isomers. The coordination difference in the ligands you can observe. Ligand isomers. Same complex compound, attachment of one of the ligand differs. Here, cobalt and cobalt. Nitro group, and this is nitroso. So there is difference in the ligand. This is coordination position isomers or ligand isomers. Here it is shown by bridge and it arises due to difference in the attachment of the ligand. Difference in the attachment of the ligand. This is coordination position isomers. You can see the linkage isomers. Pentamine, nitro cobalt 3 chloride. Pentamine, nitrito cobalt. Here the same complexes. There is difference. Nitro group is included. Here it is nitrito group. Therefore, there is difference in the colors. Coming to the geometrical isomerism. Atoms of the group arranged differently spatially relative to the metal. You're having platinum, diamine, dichloro complex. If similar, these two similar ligands on same side, then that is cis. Chlorides on same side and ammonia on same side, that is cis. If ammonia is opposite to ammonia and chlorine is opposite to chlorine, then that is geometrical isomerism. This is the cis platinum diamine dichloro platinum complex. NH3 groups on the same side. Chloride groups on the same side. One is platinum. Trans. This NH3 opposite to NH3. Cl opposite to Cl. And similarly for the octahedral. complexes. This octahedral complex cobalt, NH3 is opposite to NH3. Sorry, both of them same. This 4 are the same. These two are the same side. Then that is cis. If chlorine are opposite, then that is trans. You can observe clearly here. Yeah, cobalt, tetramine complex, chloride and chloride. Next, cobalt, here, tetramine, the chlorides. They're coming out. Here, it's the opposite side. Once if you see the diagram this way, you get your chlorine obstacle. It's both same side, not opposite. So this is about the geometrical. And the next one is the optical excellence. So today's class we have discussed about the isomers of the complex compounds, structural ionization. Example, pentamine, sulfate, cobalt, bromide complex. Again, pentamine, bromo, cobalt, sulfate complex. You can take this. Structural ionization. And coming to the hydration, water molecules, chromium hexachloride. Next, penta-aqua chlorochlorine. That is a hydration isomers. Next, linkage isomerism is explained. There is linkage difference. Nitropentamine cobalt 3 complex, nitropentamine cobalt 3 complex. Coordination sphere isomerism. Coordination isomerism. The isomers where to contain both the cations and ion complexes, and it results from interchange of the ligands between the two complexes of the same point. The interchange of the ligands between two complexes of the same complex give you the coordination isomers. We will have the polymerization isomers. The complexes having same empirical formula but different molecular disposition isomerism, polymerization isomerism. Example, diamine dichloroplatinum complex and tetramine platinum and tetrachloroplatinum complex. This all combined you get one. So tetramine platinum is one linkage, tetrachloroplatinum is one. All these combined together you get a polymer. Polymerization is one. Similarly, dichloroimine and diamine dichloroplatinum complexes. So on these two will contribute to the polymerization isomers. Ligand isomery, here are the examples. There is linkage of the ligand. The nitrogen is linked to the centimeter and oxygen is linked to the centimeter. The point of attachment of the ligand differs. Due to this, because of this ligand, the attachment, the complex differs in the color. Geometrical also cis and trans. You understood. So, thank you for today. What you have seen in today's classes, coordination compounds. Complex compounds are coordination compounds. The compounds having dative bond or coordinate covalent bond between the metal and the ligand are coordination compounds. These coordination compounds, they have special properties, that is stability. They don't lose their identity, retain their identity, even dissolve in water and in the solvent. So they have completely different properties compared to their constituents. These are the complex compounds. These are entirely different from the double solvent. And now, types of complexes you have cationic complex, you have anionic complex, you have neutral complex, so on. Next, Coming to the terms which we have discussed, complex ion, counter ions, ligands, what is a central discussed, and what is a coordination number, what is coordination sphere, and how the geometries are coming for the complex compounds, ligands, and different types of ligands, depending on the donation capacity, unity, bidentate, tridentate, polydentate. So formulas, how to give the formulas for the complex compounds. First cation, then anion, and in between the complex, again in the complex, alphabetical order, first ligands and mid-atom, along with the oxidation state. And different types of ligands, examples we have seen. Different types of metal ions we have seen. How to name we have seen. And the first theory, Werner theory, data, I have explained. And what is isomerism in the coordination compounds? Structural, stereo, structural, again, food. That is a coordination, linkage, ionization, hydration, and coordination position, that is ligand isomerism, and polymerization isomerism and explained. And coming to the stereo isomers, what are geometrical isomers? So, and in the geometrical isomers, cis and trans. Thank you, everybody. I hope you have understood this class.